All right, for this video, we're going to talk about potential energy in springs. A couple of things you need to know before we start talking about this. First off, when we mention K, K is just some constant, and it deals with the stiffness of a spring. Now, the bigger K is, bigger the K value, the stiffer the spring. So if you have a really small number, then it's going to be a really weak and flimsy spring. A really large number, we're talking like shocks on a vehicle type of spring we're dealing with. When objects are hanging, we can talk about the force of gravity is going to be mass times gravity. Just something to keep in mind when we kind of talk about some of these. Hooke's law is something that deals with springs. We really didn't talk about it when we were talking about forces. We're going to talk about it now because it's what we're dealing with. So the relationship between force and displacement, so how far that spring is going to move. So our force of the spring, that's what the F sub S is. So F sub S is the force of the spring, is equal to the negative of our K constant times by the displacement that it moves. And remember, displacement is how far it moves from rest, basically. So if you remember F sub S, like I said, this is the spring force. This is measured in newtons. It's finer tip here. K is just the spring constant. And that's measured in newtons per meter, or N over M. And then X, like I've said, is displacement. Which again is measured in M. And then the negative just tells you the direction of the force is opposite of the direction of the displacement. So when you shove in, when you apply a force inward to compress it, the force is going to push back out to try and get it back to equilibrium. Same with you, if you pull it to stretch it out, then it's going to want to snap back and pull backwards opposite of you to go back to that original position. So it's negative. When we're talking about potential energy in springs, there's a slightly different formula. So potential energy in springs is going to be 1/2 times by K times by X squared. Again, this is anytime something's being stretched or compressed. So for example, like a bow and arrow, a rubber band, a spring, anything along those lines. So now when we look at our one of two examples here. So if a spring has a spring constant of 2 newtons per meter and it is stretched 5 centimeters, what is the force of the spring? So first thing we need to do is we need to change our centimeters into meters. So we're going to do that by dividing by 100. So we should get 0.05 meters, because again, that has to be in meters. Then we just need to plug into our formula. So we're finding the force. So F of S equals negative K times by X. So negative 2 times by 0.05, which is going to give us negative 0.1 newtons of force. So it's a small amount of force because we have a very small amount of distance there. With this one, our next example, so a spring has a constant of 256 newtons per meter. How far must it be stretched to give you the elastic potential energy of 48 joules? So we're looking at the potential energy of springs equals negative K, not negative K, my formula's mixed up. It should be 1/2 K x squared. We want to know how far it needs to be stretched. So I'm actually going to start to go through and I'm going to rearrange this. So we're going to divide. Well, first thing I'm going to do is I'm going to multiply both sides by 2. So I'm going to multiply to get rid of our halves. So then we're left with 2 times by potential energy of our spring equals K times by x squared. I'm going to divide both sides by K. Switch colors. So then I'm left with 2 PES over K equals x squared. So I'm going to take the square root of both sides to give us our formula. So displacement equals the square root of 2 times by our potential energy of our spring all over K. So we can go to plug in our numbers for this. 2 times by 48 all over 256. And so when you plug this in, you get it to be 0.61 meters. That's how far you'd have to stretch our spring to store up that much energy. And that's all there is for potential energy of springs.